Right, hello folks, and welcome to number 10 in the Ozone mini videos. They realise they're not entirely tiny. Hope you're coping. Let's just do a quick bit of recall on some of the previous ideas. So you've previously met ozone. What is the formula of ozone? And hopefully you said O3. Do you remember how to do a dot cross diagram for ozone? And hopefully you remember that it's based around a normal oxygen molecule, O2, with then a dative covalent bond to a third oxygen atom, like that. So thirdly, do you remember the two steps, the two equations in the stratosphere that explain why ozone is present in the stratosphere? So the formation of O3 in the stratosphere, two reaction steps. Pause the video, see if you can write them out. Start again when you're ready. And the two steps are that initially you get the photodissociation of oxygen into two oxygen radicals, and that's due to high energy UV. And then secondly, an oxygen radical can combine with another O2 to make O3. Fourthly, do you remember why ozone in the stratosphere is beneficial to humans or life in general? Pause the video, see if you can explain. And you should make the following points, doesn't really matter what order you do, that high energy UV from the sun can cause DNA mutation leading to skin cancer if it reaches the Earth's surface. But ozone absorbs high energy UV from the sun. It's chemistry, so don't just write things in words, use equations as well. If you know, why just say that when you can write the equation that shows that process happening. So that's high energy UV. Always be clear that it's high energy UV. There's lower energy UV that passes through the stratosphere. It doesn't get absorbed in the same way. It doesn't break bonds. It reaches the Earth's surface, and that's as long as you wear your sunscreen sensibly, what allows you to get a suntan, doesn't cause DNA mutations and skin cancer in the same way. And so then we can say this, so this prevents the skin cancer problem. Make sure you use the word absorbing. So do not say that ozone blocks the UV or reflects the UV or acts as a shield against the UV. You're a chemist, so use the right terms. It's literally absorbing it. The photons get absorbed, passing on their energy to the electrons and breaking the bonds as a result. So number 5, what is the difference between that and the troposphere? Both in terms of the origin and the impact for humans. And you should say that in the troposphere, O3 is a pollutant, and it's from combustion of fossil fuels, significantly, e.g. Cars. Don't just say combustion of fossil fuels. Nobody just well, generally they don't just, pour out petrol and set fire to it. So actually link that to a human activity. So you get nitrogen oxides and hydrocarbons. Those react in sunlight. Photochemical smog. Containing O3. That's toxic. Okay, here's a question that we didn't actually directly say, but see if you can figure it out. Why does O3 not form in the troposphere in the same way that it does in the stratosphere? So pause the video, have a think about that. So now the answer is about the high energy UV radiation, and there's a kind of a bit of sort of circular logic here. So the formation of O3 in the stratosphere involves that O2 splitting to give 2 oxygen radicals. This needs high energy UV radiation. But since we have ozone in the stratosphere, the O3 in the stratosphere absorbs this high energy UV radiation from the sun. So the radiation reaching the troposphere, and be careful how you explain this. This isn't about quantity. It's not that there isn't enough radiation. It's just a bit messy. Sorry, hang on. Troposphere is not sufficiently high frequency to break bonds. Okay, so don't say there isn't enough UV radiation. There's plenty of UV radiation reaching the troposphere. It's just lower frequency UV radiation, the stuff that's not absorbed in the stratosphere. But that is not sufficiently high frequency to break bonds. Therefore, it can't smash up the O2 molecules to make oxygen radicals. Therefore, they can't react to make O3. So therefore, that doesn't happen. So since we have O3 forming in the stratosphere, we can't have O3 forming in the troposphere. Presumably, back in the early development of the atmosphere, as the plants started to photosynthesize and oxygen first appeared in the troposphere, maybe because there wasn't a stratosphere with ozone absorbing the high energy UV radiation, maybe with that radiation reaching down into the troposphere, there was ozone in the troposphere initially, but then that kind of worked its way up to the stratosphere, and now it doesn't form in the troposphere. Okay, the rest of the video is going to look at the topic of ozone depletion in the stratosphere. Depletion meaning stuff being removed, getting less. If you deplete something, you use it up. Just note, this is a bad plan. We want the ozone in the stratosphere for reasons recently described to absorb the high energy UV radiation to prevent it reaching the Earth's surface, where it can cause DNA mutations and hence skin cancer. So if there's less ozone in the stratosphere, more of that high energy UV radiation gets through the stratosphere down to the Earth's surface, where it mutates DNA and causes skin cancer. Not good. We do not want ozone to be depleted in the stratosphere. Okay, so just note, naturally in the stratosphere, you have O2 plus O forming O3. So that's ozone forming. And then you have O3 going to O2 plus O when high energy UV radiation is absorbed. This is the way that the ozone stops the high energy UV radiation reaching the Earth's surface. And so we have these things that can then go back into being ozone again. So this is a cycle. So there's a constant cycle of O3 forming. So this is ozone photodissociating. A constant cycle of O3 forming and being destroyed. And this is in balance. You can't call it an equilibrium because you can't really call it a closed system, the atmosphere. So it's a steady state. So maintains a constant ozone concentration. I should just pause at this point to say that I think ozone doesn't get enough credit. So next time you're standing out there in the sunlight, be aware of the fact that ozone is up in the stratosphere, absorbing the high energy UV radiation, which would otherwise be reaching your skin and mutating DNA and leading to skin cancer. Of course, what these reactions show is in the process, ozone dies. So it sacrifices itself to spare your skin, literally. Of course, then it's born again, only to die again. So it's a constant cycle of death and reincarnation of ozone up in the stratosphere for your benefit. So be out there, look up at the sky and just send the love up to the ozone. I don't think enough people thank it. I hope it doesn't hurt when it gets splattered by the high energy UV radiation. If you listen carefully, maybe you can hear the ozone screaming. Yeah, okay. Move on, Marcus. Okay, so that's all very good. Well, all very good. So constant ozone concentration, but ... humans. And we produce pollution. So here's the little story. Humans use CFCs, or they used to use. Not supposed to anymore. What are CFCs? Well, they're used as refrigerants, the substance in a fridge that gets pumped around and to cool things down, solvents, aerosol propellants, etc. CFCs are molecules of carbon, fluorine, and chlorine only. So in other words, they are alkanes with every H replaced by F and Cl. So as an example, sorry, I'm just checking that this is recording. Moment of paranoia. Yeah, that's good. As an example, e.g., very simple one, carbon with 3 fluorines and a chlorine. It has to have both. If it's just fluorines, it's not a CFC, it's just a CF. So it's always carbon and fluorine and chlorine and nothing else. So carbon, fluorine and chlorine only. Just pause the video a moment. What is the systematic name of this molecule? And you should have spotted that it's one carbon, so it's a methane. It's got 3 fluorines, so trifluoro, and 1 chlorine, chloro. We put things alphabetically, chloro before fluoro. So this is chloro, trifluoro, not fluoro, fluoro, methane. No numbers required because they're all on the same carbon. Obviously, if you've got more than 1 carbon, then you start having to put numbers in front of the halogens to say where they are. Why were these used particularly? They were very useful because they are non-toxic. You can literally inhale them without any seeming ill effect. Unreactive, non-flammable. So great for things like those uses, aerosol propellants, solvents, etc. Think about your aerosol at home. You're spraying on your deodorant. Ideally, the gas that's pushing out the active ingredient shouldn't be toxic. So when you inhale it, you get ill. That's not good. It should be unreactive, that it's not attacking your skin or anything, and also non-flammable, that it can't accidentally explode in a fireball. They were great for that reason. But this meant they survived in the atmosphere for long periods. Eventually reaching the stratosphere. So we can just make a little point here that most pollutants react and are broken down and or dissolve in water and get washed out of the atmosphere without reaching the stratosphere. Okay, so this is an idea you should be aware of. So just to unpack this a bit, things move around the Earth's surface in the atmosphere quite quickly with the winds blowing, but vertical travel up through the atmosphere is quite slow. It takes years for stuff to slowly work its way up and up and up in the atmosphere, up into the stratosphere. And so most of the pollutants we release at the Earth's surface, they might cause all kinds of mayhem and be toxic and all the rest of it. So think, vehicle pollution in town. But the good news is actually they're reactive enough, and that's part of the reason why they're a pollutant and are toxic and things, that they react and get smashed up, and then those fragments dissolve in water and they get washed out the atmosphere, so they don't get very far. But these CFCs, where they're so non-toxic, unreactive, non-flammable, and I'm also going to put here insoluble in water, they don't do those things. So they don't react with other stuff. They don't get smashed up. And that's what made them so wonderful, where they're unreactive and non-flammable. They're very stable. So nothing happens to them. And they're not water soluble either, so they don't get washed out. So they're just in the atmosphere. Nothing's happening. And they slowly, therefore, do that travel up into the stratosphere. So CFC started being used back in, I think it was like the 1940s or 1950s. And everybody thought they were absolutely wonderful because you could just do what you wanted with them. pumping them out in the atmosphere, as you know, through aerosols or whatever else. Nothing was happening, wasn't making anybody sick. Everything seemed absolutely fine. But over the decades, more and more of this stuff reached the stratosphere, and eventually we started becoming aware that once they get there, they do cause a problem. So in the stratosphere, CFCs are a disaster. And you need to have an explanation of why this is. So step one is photodissociation of a CCl bond. Why that one? Because that's weaker than a CF bond, right? Atom size, fluorine atoms at the top of the group are smaller, so they make shorter bonds. Shorter bonds are stronger. So photodissociation of that bond when high energy UV radiation is absorbed. So this is a bit like we were saying about why ozone doesn't form in the troposphere. This doesn't happen in the troposphere because there isn't high energy UV radiation. But once they reach the stratosphere, that high energy UV radiation from the sun is present and so can be absorbed. Right. So if you take the molecule, let's have CF2Cl2. Pause the video. I want you to just do a mechanism for that step. What does photodissociation of a CCl bond look like in terms of curly arrows, and what would be produced as a result? Okay, so we're breaking a CCl bond. That means we need to have electrons coming out of it. Photodissociation does this radical forming thing where the bond breaks with one electron going to each side. If that's what's happening, then what forms is radicals, right? One electron ending up on each atom unpaired. So we get these radicals. So radicals are formed. What's the definition of a radical? Species with an unpaired electron. So each of these have unpaired electrons. And remember, radicals are very reactive. Okay, what type of bond breaking is involved here? It's a photodissociation reaction. Do you remember the vocab? What type of bond breaking? And you should be saying homolytic bond fission. That's obviously an endothermic process. Bond breaking requires energy. Energy is coming from the UV. Okay, step two comes in two parts in the CFC disaster. So once we've made the chlorine radical, so the chlorine radicals attack and destroy ozone. Or in fact, no, let's phrase that better. They catalyze the destruction of ozone. Okay, so how does that happen? Step A, part A of step two, a chlorine radical reacts with an ozone. And do you remember what they did when we looked at the radical substitution of alkanes? Radicals grab atoms off other molecules. They kind of poach atoms off the molecule. So you get a CLO where it grabs an oxygen. Now, interestingly, that is still a radical, and you won't be expected to do full structures and dot crosses and curly arrows, etc. for this. You can just keep it at this surface level. It's a bit complicated with ozone's got weird bonding and everything, so just don't overcomplicate this. And that leaves an O2. So this is going to be an intermediate species formed in that first part that carries on into our second part of this second step. The ClO reacts with an oxygen atom to make Cl radical plus another O2. Okay, so if you're sitting there going, well, that's for handy, Marcus, just dropping in an oxygen atom. Where'd that come from? So these, remember, are present naturally in the stratosphere from the processes we looked at that form ozone in the first place. O2 getting split up to make oxygen radicals, and then ozone splitting up as well to go back to an O2 and oxygen radical. So they're just there. It's not a, it's not just a teacher coming up with a clever way of explaining something. As the ClO forms, it bumps into oxygen radicals that are present naturally in the stratosphere. So look at what's happening. Here's our, I'm back. Weird things going on there. Hang on. That's better. Here's our chlorine acting, going in. So it's a catalyst. But catalysts don't get used up. So in the first step, it is used up, but here it is again. So the catalyst regenerated. And so it can repeat A and B over and over. So the bad news is that just one chlorine radical can destroy about 100,000 ozone molecules before something comes along and terminates it. So each, now you don't need to remember that exact number, but you need to have this general sense in your head. It's not just one chlorine radical destroys one ozone, it's acting as a catalyst. It gets used up, sure, but then it gets regenerated, the chlorine radical. So each chlorine radical destroys, on average, approximately 100,000 O3 molecules in its lifetime before being terminated somehow, before termination. Obviously, that's an average. Some chlorine radicals get knocked out quicker, others take longer. Okay, so this is a bit like the reaction of alkanes with halogens. Do you remember that? When the halogen radical formed, it then went into a little two-step cycle of reacting in a way that produced the reaction between the alkane and the halogen. Look at these steps. What type of steps are these in a radical reaction? So these two steps here, do you remember your three types of radical reaction step? There was termination steps, there was propagation steps, there was initiation steps. What type of steps are these and why? And so you should say these are radical propagation steps. Why? Because we've got radicals on both sides. So both reactants and products contain radicals. Okay, you should also be able to turn two reaction steps into an overall reaction. Do you remember that? It's something about cancelling out things that same on both sides. So what is the overall effect of these two reaction steps? Have a look at them, just pause the video. Can you write an overall balanced equation that shows the overall effect of these two things, these two steps happening? Okay, and the way that you do that, so overall, so I'm just going to write them out again. We've got our Cl plus O3 going to ClO plus O2. And then we've got our ClO plus O going to Cl plus O2. No, I'm not putting the dots next to the things. You don't need to. It doesn't. You're not wrong not to put them. So the way we do this is that we add up all the reactants and all the products. So on the reactant side, you've got Cl plus O3 plus ClO plus O. And we add up all the products together, ClO plus O2 plus Cl plus O2. And then we cancel things that are the same on both sides, both the same formula and the same quantity. You can't, if you had two of them on one side and three on the other, you would have to leave one on the side where there was three and just cancel the two. But here it's the same quantity. So we've got Cl and a Cl. We've got a ClO and a ClO. So what this does overall is an O3 reacting with an O to make two O2. So a point to note here is you might look at that and you think, well, hang on, couldn't that just happen in the stratosphere anyway? In the stratosphere, you've got ozone and you've got oxygen atoms, and can't they just react together and make oxygen? So the point is this, that this is a very slow reaction without a catalyst, e.g. the chlorine radical. So although it could potentially happen up in the stratosphere, it's quite cold up there, even though it's a bit warmer than the top of the troposphere. And so it just goes too slowly to be of significance. This should remind you of the definition of a catalyst. So what was the definition of a catalyst that kind of fits with the fact that the chlorine radicals are giving us these steps that make for a faster reaction than just the ozone molecule directly reacting with an oxygen atom? And hopefully you've remembered that thing, that it provides an alternative route for the reaction with a lower activation energy. So increasing the rate without being used up. So this is a perfect example of that. If you think about it, if the reaction that's being catalyzed is the O3 plus O going to 2O2, the chlorine radicals provide an alternative route, i.e. those two steps, A and B. And that then makes the reaction happen much faster than it would otherwise. And the reason for that is it has a lower activation energy. You should be able to illustrate that. So on an enthalpy level diagram, do you remember these? You've got enthalpy, H. You've got the progress of the reaction. And then let's say you've got your O3 plus O here. I'm going to say it's an exothermic reaction. So you've got your 2O2 down here. Just pause the video in a moment. Can you remember, how would you draw on reaction profile lines, if you remember what that means, that allow you to illustrate how this reaction has a lower activation energy if it goes the route with. Okay, I paused. Doing it again. Okay, I think we're still recording. I hope this has worked. Technology. The Wi-Fi was dropping in and out at college for some reason, but hopefully we're back. We're nearly done anyway. Okay. So yes, this diagram, right, anyway, I'll tell you the answer. You draw on a curve that goes from the reactants up to a peak and then drops down to the products. And you say, if we do a line at the very top of that peak, the gap, the jump up from the reactants to that peak is the activation energy, EA. So this would be without the catalyst. I.e. the Cl dot. If we had it with the catalyst, then let's have a green line. We would go lower, and what we can actually do is go, well, we go in that sort of step A and that step B. It doesn't really matter how high they are relative to each other. So this is the kind of A and then B from our two-step process that the chlorine radical introduces. And so now we can go, well, okay, this is our sort of peak. If your two humps on the camel's back there are different heights, you just do it to the highest one. And so this would be the activation energy with the catalyst. Okay, we're going to be starting the second year with discussion more about reaction rate and catalysts and activation energy and all that kind of thing. So, you know, this will be further developed. The only other sort of question that is obvious to ask here is, do you remember you learned about different types of catalyst? If you think about the chlorine doing its thing here, what type of catalyst do you think the chlorine is acting as up there in the stratosphere? There's two types, have similar names, just the prefix changes slightly. And hopefully you're shouting, it's a homogeneous catalyst, Marcus. So the Cl dot acts as a homogeneous catalyst. Why? Because both it and the reactants are in, well, the same state, but we might as well be literal. They're up there in the atmosphere in the gas state. Why? Because they're in the atmosphere. So they're just behaving as gases. Okay, right. So there's quite a lot there. So you've got to have this idea that the ozone in the stratosphere is normally just cycling through this birth and death reincarnation process as it absorbs UV light, maintaining a higher concentration. But if you chuck in something like a CFC to the atmosphere that gets up to the stratosphere, it can then photodissociate to make a radical like the chlorine radical. And that then does this two-step sequence. It'll look complicated to start with. I'll keep on saying this. Don't expect just to watch the video once and go, I know that now. That is not how learning works. It takes a while for our brain to sort things out and sift and organize and make connections, and that often requires you to revisit stuff. So expect to just have to scan through this again a bit, maybe make some notes, revision, poster or whatever, mind maps, flowcharts, whatever works for you. Maybe some flashcards for the facts that you need to memorize. Anki, hey, moving on. So you've got this two-step process of the chlorine radical initially reacting with ozone to make the ClO, and then that reacting with an oxygen atom to regenerate the Cl. In the process, we knock out a couple of oxygens, which overall are equivalent to an ozone reacting with an oxygen atom to make 2O2, something that goes very slowly on its own, but much faster with the chlorine radical, with chlorines acting as a catalyst, giving an alternative pathway with a lower activation energy. Okay, there are just a few other bits and pieces to say here. One is that you should be able to put into words why this is a problem. Why is this an issue for humans? So just pause. Think what we said before about what the benefit of ozone is. So how could you string all this together? Why is CFCs going into the stratosphere a problem for humans? See if you can bash out a few bullet points. Pause the video. Start again when you are done. Okay. So you should say so CFCs reaching the stratosphere make Cl radicals. Okay. If it was an exam, always remember equations and stuff are better than words. So you could have, e.g., CCl2F2 to CClF2 plus Cl dot. And then Cl radicals catalyze the destruction of ozone. And so you could put in the equations for that as well. Cl plus O3 goes to ClO plus O2, and then ClO plus an oxygen atom regenerates the Cl and another O2. And so then you can make the point this causes the concentration of ozone to fall in the stratosphere, to fall. So what? So less high energy UV radiation from the sun is absorbed. So more of this radiation reaches the Earth's surface. So more DNA mutations, more skin cancer. Okay, just notice then, if you get asked why does CFCs reaching the stratosphere cause a problem to humans, you need to make a clear link. Yes, the CFCs reach the stratosphere, and the problem for the humans is skin cancer, but how do you get from one to the other? An exam question will expect you to make a clear chain of logic, and you could add in some extra detail like here, like when they reach the stratosphere, they absorb high energy UV radiation, photodissociation, and give the equation and so on. And then so what the chlorine radicals, that catalytic process, and give the equations, and then so what about that process, and just so until you've made this clear chain of logic. Okay, a final little bit of No. One. Yeah, now let's just do a quick practice then. See if this idea that radicals can catalyze the destruction of ozone, see if you can put that into practice. Other radicals can also have the same effect. In the troposphere. E.g. OH radicals, not hydroxide ions, but OH radicals. So use equations to suggest how OH radicals catalyze the destruction of ozone. Okay, this isn't something completely new, so I'm not just setting you an impossible make-it-up challenge here. The point is that all radicals follow a similar sequence. So just from what we said about the chlorine radicals, how could you adapt that to show how other radicals, in this case an OH radical, can catalyze the destruction of ozone? So pause the video, have a little play, see if you can come up with some ideas that prove that point. Okay, and so all you should do is say that you can have the same two-step cycle. So instead of a Cl dot, you've got your OH reacting with ozone and stealing an atom from it. Now this freaks people out because instead of water, H2O, if you grab an oxygen, you get O2H. And they look at that and go, it's not possible. But just go with it. If you've been told that something is, going to do a similar thing, just run with it. Suspend your disbelief, as they say. Having grabbed an oxygen off the O3, you'll be left with O2. So the OH is just being a radical. It's grabbed an atom off the O3. It's an oxygen atom, so it gains an extra oxygen. And then, just like for the chlorine, the O2H will react with one of those naturally occurring oxygen atoms in the stratosphere, which pulls the oxygen back off, takes us back to OH, plus another O2. So we can say that our OH the OH is used up, but then reformed. So the OH provides an alternative route. Now, if we're told that it is a catalyst, then it must be an alternative route with a lower activation energy. So if you know something to be true, you can just bring in anything that therefore must be also true. But it provides an alternative route with a lower activation energy. And do you remember what the overall reaction was? The O3 plus O goes to 2O2. Oops. Reaction. So it doesn't matter what the radical is. You just map it in exactly the same as the chlorine radical. Everything else is true. You just replace the chlorine radical with whatever that other radical is. Okay. Finally, you don't need to say much about this, but the solution to the problem. Number one, don't use CFCs. Of course, that would just mean, don't have fridges, don't have aerosols, and humans like those things. So instead, replace them with alternatives that, well, think about it. From what we've said about the problem with CFCs, logically, what would you want to be true about your alternatives? There's kind of two possibilities here of things that we can use as replacements for CFCs. I don't mean pick a substance. I mean properties of the substances. What would have to be true about the way they behave that mean they don't cause the same problem? Whatever we put in our aerosol or our fridge, etc. So just pause and see if you can come up with anything. And the two options here are that break down / dissolve in rain, etc. in the troposphere. So they don't reach the stratosphere. Or have such strong bonds, have very strong bonds, so they don't photodissociate and form radicals. Even if they do reach the stratosphere. Okay, so the problem is that you reach the stratosphere and photodissociate and make a radical, and that radical then goes to work catalyzing the destruction of ozone. So if you can have a replacement that either never gets to the stratosphere, or if it does get to the stratosphere, doesn't form radicals, then you're okay. Of course, the problem with that second one is that maybe if they don't react in the stratosphere, they'll carry on up further in the atmosphere, and then something will happen and it will have catastrophic effects that we haven't imagined yet. But hey ho. Okay, that is this video done.